In this topic, we'll uncover three quiet workhorses of modern crypto: hashes, MACs, and randomness. They don't grab headlines like encryption, but they largely decide whether PKI and TLS are actually secure or just look secure on paper. Before we build PKI or TLS, we need three core ingredients: hashes, MACs, and randomness. Hashes act like fingerprints for data. Change even one bit, and the fingerprint changes, giving us integrity. MACs, or message authentication codes, add a shared secret key on top, so we can also verify who created or modified that data. Randomness is the fuel. Without strong, unpredictable randomness, keys and protocols can often be guessed or quietly broken. A hash function takes any kind of data and deterministically squeezes it into a short, fixed-length fingerprint called a digest. Good cryptographic hashes have three key properties. Preimage resistance means that given a hash, you can't feasibly recover the original input. Second, preimage resistance means that given one input, you can't find a different input with the same hash. Collision resistance goes further. It should be computationally infeasible to find any two different inputs that produce the same hash. When you're designing PKI or TLS today, it helps to think in three generations of hash functions. First, MD5 and SHA1 are finished. We have practical collision attacks, so any use in signatures, certificates, or integrity checks must be treated as insecure and removed. Second, SHA2, especially SHA256 and SHA51212, is the current workhorse. There are no practical collision attacks, so this should be your default for new deployments. Third, SHA3 exists as a structurally different backup. Reach for it when you want algorithm diversity or some additional future proofing. When an enterprise says secure data, it really means securing the entire lifecycle of how data moves and changes. Certificates bind identities to public keys, so systems know who they're talking to. The TLS handshake then uses those keys to agree on fresh symmetric keys and verify that no one is tampering with the connection. On top of that, software supply chain controls use signatures and hashes to ensure the code and files flowing through this environment haven't been modified before they ever reach production. Hashes are great at telling us if data was modified, but they have a big weakness. Anyone can recompute the hash. A plain hash gives you integrity, but not identity, so you still don't know who actually created it. A message authentication code fixes this by mixing the data with a shared secret key. Only someone who knows that key can produce a valid MAC, so you get both integrity and authentication. HMAC is a standard way to turn a regular hash into a keyed integrity check. We take a message and a secret key, run them through a specific construction around a hash function, and get a verification tag. Anyone who knows the shared key can recompute the HMAC over the received message and see if the tag matches. If it matches, the message is intact and came from someone who knew the key. Compared to plain hashes, HMACs are designed to resist common attacks like length extension. Randomness is the invisible foundation of almost everything in cryptography. When randomness is weak or predictable, attackers can often recover keys, forge sessions, or replay traffic without breaking any math. We rely on high-quality random values to generate keys, to pick nonces and IVs, and to create unique ephemeral session states. When that randomness fails, the entire PKI and TLS stack can quietly fall apart. Randomness in real systems is layered. At the bottom, the operating system collects messy, unpredictable events: keystrokes, disk timings, hardware noise, CPU features. It stirs all of that into an entropy pool. On top of that, system random number APIs like devs, urandom, or bscript-genrandom stretch this entropy into as much cryptographic quality randomness as you need. Finally, crypto libraries and applications consume it for keys, nonces, and tokens. The key rule is simple: never roll your own randomness. Always use the OS RNG. In practice, you'll see two very different families of random number generators. General-purpose PRNGs are designed to look random statistically. But if an attacker can observe enough output or internal state, they can often predict future values. That's fine for simulations or games, but not for keys. CSPRNAs start from high-quality physical entropy and use cryptographic constructions. Even if an attacker sees a lot of output, they can't feasibly reconstruct past values or predict future ones. That's what you need for PKI, key generation, and TLS. Weak randomness is one of the fastest ways to destroy otherwise solid cryptography. If you reuse nonces in protocols like TLS or SSH, attackers can combine ciphertexts and algebraically recover session keys. When embedded devices have poor random number generators, they may ship millions of RSA or ECC keys that are partially or fully duplicated. Once one device is broken, many others fall with it. Predictable tokens like password reset links or session IDs let attackers guess their way into accounts. So strong algorithms are not enough. You must also engineer strong entropy sources. Now let's connect these building blocks to the TLS handshake. First, both sides generate fresh randomness with a CSPRNG. Those nonces and ephemeral keys drive the key exchange and ensure every session is unique. Next, the server proves its identity. Its certificate chain and signature are verified using hashes, so the client knows it's talking to the right endpoint and that nothing was modified. Finally, once keys are agreed, MACs or AEAD modes protect the handshake transcript and all subsequent records, providing integrity and authenticity. To turn these concepts into habits, bake them into your standards and tooling. For hashes, mandate SHA-256 or better in code reviews and static analysis, and schedule scans to find any remaining MD5 or SHA-1. For MACs, default to HMAC or AEAD cipher suites in your TLS and application configs, and disable legacy options. For randomness, forbid homegrown generators in your secure coding guidelines and require vetted OS or library CSPRNG APIs in every design.